Our next speaker is Dr. Jay Boehner, who's a professor at the University of Texas and as well as the director of the Environmental Science Institute there at UT. Dr. Boehner and his team have been leading important research on urban groundwater challenges, and we've asked him today to discuss some of the results of that work and highlight some of it for us today. Please join me in giving him a warm welcome to the stage.
Thanks for that intro, and I also appreciate the invite to come and speak to this group of groundwater managers. I think from listening to the talks the past few days, I'm always really impressed with how many aspects around water resources there are that you all have to integrate in your work on a day-to-day basis, and my work pales in comparison to that. So what I'd like to do today is share with you some perspectives from our research in my group and all these people I've acknowledged down at the bottom. What are some of the challenges we've faced this century in terms of groundwater in our urban centers? So let's start with sort of an outline of what I'll present around these multiple impacts on urban groundwater this coming century. First, there's a warming atmosphere, and I think what I'll show is that our aquifers are very susceptible to those, and those changes that are to come based on model projections will be unprecedented, those impacts. We'll talk about a growing population and expanding cities. I won't talk about this one much because I think we all know it, we're all in it, right? And so 7 of the 15 fastest growing US cities are in Texas. All 7 of those are suburbs of either Austin, San Antonio, DFW, or Houston. Probably the majority of us have been there or go there, so we all know about this rapid expansion, but nonetheless, it is going to be a big impact on our water resources. And then I'll define urban stream syndrome, which some of you may know about. We'll talk about groundwater, surface water interaction. The ubiquitousness of groundwater, surface water interaction means that urban stream syndrome will become urban groundwater syndrome, right? That's inescapable anywhere where you have groundwater, surface water exchange. And then finally, I'll talk about our aging infrastructure and what impacts that will have, and ask the question, what are the timescales of impacts on aquifers and surface water here in our state? We really don't have good constraints on that, and I'm going to offer today a new tool, a new way to actually try to reconstruct that. All right, so starting with a warming atmosphere, this graph shows the past 3 decades of drought in red and spring flow in blue from the Edwards Aquifer at Barton Springs. And down is dry, up is wet in terms of the red drought index. And what you can see is that there's a hand-to-glove fit between the drought index and spring flow from the aquifer. All right, showing that this aquifer is very susceptible to changes at the surface, including changes in our climate. If we look at the Edwards Aquifer and think of all the vulnerabilities, there are several big ones. We've got that it's karst, that produces fast flow paths, so contaminants at the surface can make it quickly underground. It's a very shallow aquifer, so those fast flow paths are also short flow paths. That accelerates the arrival of contaminants underground. And it's in a rapidly urbanizing region, the effects of which I'll be talking about today. And it's in a drought-prone region, which we're talking about now. Right, so these 4 different things, what I like to call for the Edwards Aquifer, the quadruple whammy. How will this quadruple whammy change as we go forward in the 21st century? Are these impacts going to be, they're synergistics. Will they continue to be static and synergistic, or are they actually going to change, and will that change the synergies between them? So first, starting out with what the 21st century will look like in terms of drought and recharge to these aquifers, one metric we could look at will be how hot it is. The hotter it is, all other things being equal, drive off more soil moisture, and this will have a bigger impact on drought than at current if the temperatures increase. So we're going to take the metric of the number of 100-degree days a year that we will see in various parts of Texas. So these are model projections, computer simulations to model atmospheric circulation and the impacts and the outcomes. And this is for the last 3 decades of the century. This is from the Fourth National Climate Assessment. And we could see here, obviously, Texas, Oklahoma, and Kansas. And the legend on the bottom is showing the change in number of 100-degree days for a given year. And if we look at the region we're in now, it's a little bit washed out here, but we're right here between 80 and 90 more days a year. Notice that's the change, the number of 100-degree days. It's not the total. So we have to look at our recent climate, our present-day climate. If we go back 15 years, average the number of 100-degree days for the past 15 years, there are 43 of those in Austin. So 43 plus 80 plus, right? So 123 days, that's 4 months, all right? That means 4 months out of the year, it'll be over 100 degrees. That means we're gonna have 4 months, every June, July, August, September, every day those months? No, there's cool and warm trends in any climatic regime. So those 100-degree days, those 123 100-degree days will be spread out over the calendar. They will probably start in April and extend all the way to November. That's more than half the year in which our climate will give us the heat to get over 100 degrees on any given day. That's going to have a big impact, and this is for a high carbon emission scenario, right? One useful thing for these computer models that project forward is you could sort of put in what are your desired future conditions, how can we get there? So you could come up with a low carbon emission scenario, right? One in which technological, policy innovations, et cetera, lead us on a different track. And in the low carbon emission scenario, we see a very different future Texas. It still warms no matter what because of the carbon that's already in the atmosphere, but in a low carbon emission scenario, it's a much less dire outcome, so to speak. Currently, we're closer on track to the scenario on the right than we are to the scenario on the left. Right? A key outcome of this, increased heat, as I said, decreased soil moisture. That means for a given drought, it would be more intense, it'll last longer, and there will be more droughts that will be triggered than would ordinarily if we didn't have these temperatures. So the changes that we see going forward in the 21st century in terms of drought and how it controls recharge to our aquifers, the changes will be unprecedented, not like anything we've seen in terms of drought impacts in the past. So now on to impacts of impervious cover on streams. There's 2 key factors I'll talk about. The first is impervious cover, and the next is riparian zones. And impervious cover, right, when we take the filtration capacity of the natural landscape, that is soils, vegetation, trees, all have the ability to purify water. That's an ecosystem service. If we take those away and replace it, such as in this case, with essentially 100% impervious cover, we remove that natural ability of the landscape to filter and purify the water. This is especially intense in the riparian zone of streams, right? But riparian zones, we're talking about these bankside zones on either side of the aquatic zone. And these are particularly sensitive to the removal of the natural filtration capacity, replacing it with impervious cover, because it's those riparian zones that are actually having the last line of defense, if you will, to filter shallow groundwater and surface runoff before it makes it into our streams. And here's an example of a riparian zone. We'll talk about it in a minute, but I'll define for you, many of you know what urban stream syndrome is. It's a good catch-all term to talk about all the things that can besiege a municipal water supply, and it applies to just about every city in the world. And it's water quality, it's stream morphology, stream flow, biodiversity, et cetera. And here we are looking at this zone in a watershed in East Austin, and Boggy Creek. So Boggy Creek is saying to us, take a look at my riparian zone. Not much of a riparian zone, but it's the only one I got. That's if Boggy Creek was channeling Supertramp, but unfortunately it's not. And we'll take a look again at Boggy Creek right here in East Austin. This is showing road densities in various Austin watersheds. And so this allows us at a glance to see the extent of urbanization in these watersheds. You can see how different they are. Austin's kind of providing us with a nice natural laboratory where we could do analyses for a given watershed with a similar geologic bedrock, soils, et cetera, but the main thing that's changing is the extent of urbanization. And we'll be comparing that for many of these watersheds, including in Onion Creek, which is going to be our rural end member. You can see how spaced out the road density is there. Then we'll go near the downtown area, right? Here's downtown Austin, Colorado River, where we get our municipal drinking water from in Austin, and both Boggy Creek and Waller Creek will be our urban end member, and then we'll look at Bull Creek, which is a recently and rapidly urbanizing end member. So we'll keep those three in mind, Onion, Waller, Boggy, and Bull, as we go forward here. And so municipal water infrastructure degradation, something we're all familiar with. It occurs. How much does it occur? Where, when, how, and why? And on what timescales does it occur? Let's start addressing that now. And if we look at this scene here, notice the first responders on the right. This is, as we'll see, we're coming to something. Is it Made of the Mist in Niagara Falls? It's infrastructure degradation in Austin, and this warrants a first responder and immediate response. But if you think about it, for every one of these things that require such a response that are so evident, there are countless numbers that are occult and underground and that go undetected. How might we be able to track and understand those and their impacts? Well, let's talk about what are the possible sources of these impacts. We're in Boggy Creek, this urbanized watershed. We saw high flow and changing water chemistry during a drought. On the left is before this leak, we think, we're looking at here, a municipal water supply leak that was revealed by our monitoring. So normally it's just sort of this trickle in Boggy Creek. And during the same drought period, July to October, in October, we're still in drought, and now it's almost a raging torrent, right? A much, much higher flow, even though there's been no rainfall for months. And monitoring has revealed this high flow. Monitoring is also at this one site, and monitoring has also revealed chemical composition of that water that is very similar to the supply side water of our municipal infrastructure. Now, also in Boggy Creek at a different site, but still during that 2024 dry period, there's another municipal leak where we have much higher flow than normal. This is normally just a trickle. And now I'll show you some chemical and bacterial information that indicates that this is a leak of a horse of a different color than the previous one, same watershed. And here we see some very high E. coli bacterial concentrations that reveal this to be a wastewater leak. All right, so here we're going from February to 24 into early 2025 and monitoring this on a regular basis. Notice this is a log scale. This is E. coli concentrations. For decades, Boggy Creek has been compromised. It's one of the most understudied, underserved watersheds in the city of Austin. And it's been typically around, for this log scale, hundreds to thousands of E. coli unit concentrations, which is already a very degraded system. But as we monitored it, we saw that it was increasing and increasing. And finally, again, note the log scale, we're up close to a million counts of the E. coli concentration. And this and the high flow tipped us off that there was not just, this is not a municipal supply side leak, but this is a municipal wastewater leak. And we, with the City of Austin's watershed protection, we identified that leak, and watershed protection went about fixing that leak. And as you can see, right after that leak was fixed, we actually see in the creek very low concentrations of E. coli. In fact, for at least a month, it was below limits for recreational use. That means after decades of this watershed being compromised, it's now serving, at least temporarily, as a usable water amenity for the neighborhoods, communities that live in this watershed. So from here, now that we've identified that it's not just the municipal infrastructure, it can be supply side, it can be waste side as well, we're now going to talk about how we might be able to trace this municipal water input into these natural hydrologic systems in both space and time. And so to do it, we're going to apply the isotopes of the element strontium, and the isotope ratio is expressed as 87SR, 86SR, but I'll just call it, we'll see that symbol, or I'll say strontium isotopes, to tracing urban hydrology. And this is, we're able to leverage the variations in geologic units. All other things being equal, older rocks have higher strontium isotope ratios than younger rocks. So as we look at this geologic map of Texas and fondly appreciate that we're sitting here on the Edwards Plateau, as you know, this is a 100-million-year-old limestone terrain, the plateau, and this will produce, through erosion, weathering, contribution of strontium from the rocks into the dissolved ion load of the streams. That strontium will have a relatively low value for its ratio. Now, by contrast, if we go to the Llano uplift, and we know there are billion-year-old rocks there, and that imparts high strontium isotope ratios to the Colorado River, which is Austin's municipal supply. All right, so Austin's municipal supply should have a high value of this isotope ratio, and Austin's local creeks draining the Cretaceous limestone should have a low value. Now let's look at the data given this intro. So we have strontium isotope ratio on the y-axis, population density plotted on the x. For all the different watersheds we looked at that road density map of, and you can see whether we look at road density or population density, we see the same results. A very strong positive correlation between the two, indicating that there is an end member up here and an end member down here, and if you mix those end member waters together, you could account for the variability for all of these watersheds. And in fact, if we look at municipal water and the Cretaceous limestone, that's exactly what the results tell us. And so it also is consistent with, remember, Onion, which is very low, is our rural watershed. Bull is our rapidly urbanizing one, it's higher. And then Waller Creek, excuse me, is very high. And if we actually do that mass balance calculation, the mixing for these urbanized watersheds, we find that up to 90% of base flow can be accounted for by leakage and irrigation from the municipal infrastructure, 90%. That's a high percent. 90% of all the flow in the creek. On what timescales does this municipal water infrastructure failure occur that we're talking about? Clearly, present day, a lot's getting in there. When did this happen? How did it happen? Was it slow, gradual? Was it episodic failures? When did it start? What caused it? Without a time series of knowing water quality against time, we're not able to answer this question. So that's where we're going next. How can we develop a proxy for how water quality in these watersheds have changed through time? Because if we could understand this, it will help us figure out how to build resilience into all of the new developments and all of these rapidly expanding cities that we see in Texas. So to do this, we're going to look at trees that grow right on the banks of these streams in Austin. And here's bald cypress tree right on the banks of Onion Creek in South Austin. There's a person for scale. And these trees put sometimes the majority of their roots right into the stream, so they're taking up stream water, the strontium that is following calcium around into the wood cellulose year by year is carrying with it the isotope signal of the stream at the time that part of the tree formed. So that's where we're headed with this. Can we use them as a record of past water chemistry? These trees in the rural watershed, are very sensitive recorders of past droughts, sort of the classic application of dendrochronology to past climate. But we find in the same species of trees in the urban watershed that they're insensitive to drought. We infer that that's due to the large amount of water coming from the leaking and irrigating municipal infrastructure. Whether there's a drought going on or not, that's always in the background. So perhaps this is a positive unintended consequence of urbanization, that the riparian ecosystem has climate resilience due to this leaking infrastructure. And we, of course, have to weigh the positives against the negatives. All right, so we're positing that we could use riparian trees as a record of past water quality changes by taking cores from these trees, microscopically examining these cores, and seeing year by year and counting back through time. And so if we're going to develop this water quality proxy method, we ask the question, does the chemical composition of tree rings reflect the water chemistry of streams through time? And we're going to try to ground truth this with the test in the modern system. And then we'll use the dendrochronology to count backwards through time and extract a given ring for a given year and measure its isotopic composition. Well, here we are in the 21st century, trees and streams. So it's strontium isotopes for Waller, Bull, and Onion Creeks. And right here we could see the tree values for the 21st century are in these rectangular bars. The water are the solid circles. So we could see for Waller, with one outlier exception, for Bull and for Onion, the tree rings today, the last couple of decades of this century, reflect the water composition we have for the last couple of decades this century. All right? This is indicating that modern tree rings reflect the strontium isotope value of the stream water from which they grow. So at least it would have to pass this test if it's going to be useful as a proxy. Right? So having passed the test, we'll go onward with the proxy and ask the question, was the increase in urbanization in Austin over the past century, was this captured by the tree ring isotopic composition? So we're first going to look at the Bull Creek watershed. Remember, that's the rapidly urbanizing watershed in northwest Austin. And on the left-hand y-axis is impervious cover percent, and the population density is on the right-hand y-axis. And we're going from back to the 1940s up to today. So if we reconstruct population density in this watershed, we could see that it really started skyrocketing in the 80s and 90s, and impervious cover followed suit. So this is really to say, no matter what measure of urbanization we look at, we could track the growth and expansion in the age of the infrastructure. And next, we're going to put on here the tree ring values, and there'll be those rectangular bars again. But first, I just want to point out, remember, municipal supply water is the high side, where things are trending upward on the 87, 86 axis, and the Cretaceous limestone is down low. Right? So natural water should be down here. Water altered, natural stream altered by having municipal water being put into it should be up there. And here now are the tree ring, these rectangular bars. And you could see that they're showing this pretty rapid increase as a function of time. So this is fully consistent with the use of this as a proxy for looking at infrastructure degradation. And what we can also put on here, the left-hand y-axis is a new one there, municipal component in stream in terms of percent. How much municipal water is in there in terms of percentage? And what we could see is that it's a few percent over time, 10% over time. And stream water in these urbanizing watersheds can be chemically altered after as little as 5 to 10% impervious cover. Right? So 5 to 10% impervious cover starts increasing. We see that the tree is responding and giving us a record of water quality on that time scale. All right, so to finish this off, we're going to look at Onion Creek and Waller Creek. Remember, Onion is the rural and Waller is the fully urbanized watershed. We're going to look at their histories. Again, impervious cover and population density is our two y-axes. We'll look at those first. And Onion Creek, it's this rural watershed. It's really not much happening over long periods of time, like in forever. I'm pretty confident that that record would go all the way back into the year 1055. We would see it flatlined like that. Right? But now, of course, the growth of Waller Creek, population density and impervious cover. Remember Waller Creek, those of you from Austin, you know, yeah, that's downtown Austin. And so that was part of the core of when the city was rapidly growing back in the early part of the century. Now, if we put the Onion Creek strontium isotope record of the tree rings, the tree goes all the way back to 1840s, and we see a relatively constant and flat value, which is consistent with not much happening to perturb the water quality in that rural watershed. But if we now look at Waller Creek trees, we'll put those in here, and where do you think the Waller Creek trees are going to be? So is that like we're number one? Is that what you mean? Municipal water supply, as a reminder. And look at the Waller tree. Each of those different colors are different trees in the same watershed, and that we could see that those trees, unfortunately, don't go back to the 1800s. They're on the banks of Waller Creek, and they go back to about 1940, right? But it looks like that by 1940, this watershed was already strongly influenced by municipal water inputs. And if we consider these two dashed lines, water infrastructure constructed 1920, by 1940 we're already seeing the impacts. This poses the question, if our model and inferences are correct, does that mean that it only took 20 years once the infrastructure was built for that human activity to alter Waller Creek? That is quite rapid. So I'll leave you with some takeaways here about the resilience of urban water supplies in 21st century Texas. Decreased aquifer recharge due to a warmer atmosphere. Those changes, as I mentioned in the talk, will be unprecedented. Decreased water quality in groundwater and surface water due to the continued rapid growth of cities, increasing impervious cover, and the aging and failing infrastructure, and the water systems may degrade in as little as 2 decades from the time the infrastructure is developed. And then consider also the costs, right, of treating and delivering all of that makeup water. If we have to pump and treat 20% more water every year to get it to the homes that need it because of these losses, those are impacts in terms of dollars, in terms of carbon footprint. But I want to leave with some paths to solutions. Kind of easy for me to stand up here in my armchair. I probably should sit in this armchair and just wave my arms around. Hey, here's ways that things could be changed. But I offer these nonetheless. Be really interested to hear what you think about them. Right? The kind of high-resolution monitoring I was talking about in terms of our hydrologic systems and Austin area watersheds to track this infrastructure failure, I think could have some big payoffs in understanding how, where, when, and why it's failing. And a lot of that is being done here at UT Austin through a project called Cressel, in which we're engaging with communities to co-produce this kind of research. And then we have to put, I think, a lot of thought into planning the growth of urban centers before they're developed. How can we get out in front of it from the lessons we learned from how the infrastructure has not worked in the past for us? And there are going to be some trade-offs in designing that infrastructure resilience. But personally, I think that resilience is much needed, and we have to really seriously look at and consider those trade-offs. And then the last thing I'll leave you with is the limits on impervious cover. I think that's, to me, I think it's a no-brainer. I think it's a proven solution. It's worked in our region, in our aquifers, not everywhere, but it's only been tried in a very few examples. But where it has been tried, it's, I think, a smashing success story. So with that, I'll be happy to answer any questions and point you to these resources. Thanks.
Do we have any? Yes, John.
Yeah, good question. I don't have a quantitative answer for you. It has been looked at. I could point you, sorry? Oh, the question is, urban recharge has been both blamed for degrading water quality, but also heralded because it helps maintain spring flow during times of drought, right, if you put more in. So I could point you to some papers that will have that answer. Wang et al. 2012, Journal of Hydrology will actually have that. But what I'll also point to is that during these intense droughts, spring flow is not where it needs to be. So what that means, what that tells me is we're not doing enough of it, and then what's that trade-off if you do so much of it, more of it, will you see the water quality degrade as well? And if we look at those projections for the late 21st century, it may not matter. We may not be able to even assess the quality of the water because spring flow may be so low as to not be measurable. Yeah. Thanks for your question, John. Yes. Anyone else? It was very effective. They went like this. They got my attention. Or you could just go like this. And another question? Why weren't there trees growing on Waller Creek earlier? Okay, so here's a short legend, has it. I've never seen this story documented, but I've heard it told by urban foresters on the UT campus, that the trees at UT were all cut down during the Civil War to build a fort because there was a Union ship sighted landing in Galveston, and the person in charge on the Confederate side here in Austin said, we need all these trees. So those trees were, if they were along the banks, they were taken down. And then it wasn't until the 1930s that someone single-handedly was so determined, someone who worked at UT, at repopulating. They brought in seedlings from outside and started planting them in the 1930s. Yeah. And I wish I could tell you why we don't have older trees along Bull Creek either. And that may be due to a combination of flooding, taking them out, as we saw in the Guadalupe River on July 4th, the devastation out there. We're trying to actually recover some of those to see if we could get drought and flood records for that part of the Guadalupe River. And it's been really tough sledding, being able to identify old enough trees, because it looks like a lot of them have just been taken out. And so flooding, Confederate war generals, flooding, and logging for a whole variety of commercial purposes are probably in reverse order the most important reasons why we don't have those trees as old as we would like them. All right, thanks for your time.